Now, Hilda throws a die, or a die means dice singular, one dice, okay, one die, and records the number of sixes that she gets after various numbers of throws. She records the results in the following table, okay? So, number of throws, calculate the relative frequency at each stage that Hilda recorded, okay? So, we touched on this one yesterday. What you do is this: relative frequency is basically how many times we get what we wanted. So in this case, we're looking for the number 6 to come up, aren't we? So what I'm trying to get at here is this: if I was to extend this table down, and what I'm going to do is what's called the relative frequency. So I'll just make this happen for a minute, like so. Now, and across. Okay, so relative frequency. Now, what relative frequency means is technically it's 2 out of 20. You got 2 heads out of 20 throws. You got 6 out of 50. You got 13 out of 100. You got 35 out of 200. Yeah. You got 91 out of 50. 500. You got 1060 out of 1000. And finally 332 out of 2000. Now here's what I want each one of you is to grab your calculator, and you're to do one calculation for me. Barry, you do the first one. No, you do the second one. Paul, do the third one. Ryan, do the fourth one. Aaron, do the fifth one. Who have I not given a number yet to? Ben, do the sixth one. Juan, do the seventh one. I want you to tell me what they are in decimals. Put up your hand when you have an answer for me. Yes, which one are you? What you get? 0 point? Okay. Yeah. Which one are you? Okay, Paul. 0 point? For which one? That one there. Okay, who's the next one? For 0.175. Yeah, next one after that. Who's got the other one? For which one? This one here? Okay, and after that? 0.16, and after that? 0.166. Now that's interesting, okay? So, just gonna do here is you can leave those if you can leave those as broken down fractions if you wanted, but the real answer would be if we could have it in decimals, okay? Because we can compare them. So there we go there. So that's it. Now, guys, what we're gonna have next is when you have a dice, okay, and a dice is something looking like this, I suppose. And there's your dice there, okay? And it's a cube. Now, how many times is the cube going to land on number 6? So 1, 2, 3, 4, 5 can be on the bottom, and 6 is at the front. So I'll just get rid of the ones that are invisible, okay? So what did you say? 1 over 6, okay? Now 1 over 6, when you put that in your calculator, is what percentage of the time? 16.67% of the time. Yeah, it keeps on going forever, but we can't draw them all, so we'll just say 6.67, okay? Oh, sorry, 0.1667, excuse me. Now, that's 16% of the time, or 16.67% of the time. Now, what happens here, guys, is look at this. What happens if I get a dice and I roll it once? I roll the dice once and I don't get a 6. Does that mean the probability of getting a 6 is 0%? No, because I only rolled it once. If I roll it 12 times, yeah? If I roll it 12 times and a 6 only turns up once, that's 1 in. But that's much smaller than 1 in 6. It's do you think rolling it 12 times is rolling it enough times to be accurate? No. So look at your results up here. This is what's going to come up in statistics, okay? So I just wanted to make you aware of it earlier on. When we only rolled it 20 times, see, the real answer is 0.667. Do you understand? That's the real answer. Is 0.1 near that? Not really. 0.12? It's getting closer, isn't it? So the more we throw it, the closer it seems to get. And then we go above it for 200. 200 slightly out, isn't it? It's too big. 500 is too big. And eventually, by the time you get to 1,000 and 2,000 throws, what you notice? Get more accurate. So the more you try an experiment, the more accurate it will be when we average it all up. Okay, so this is roughly 1 in 6 chance of it happening, which is what we expected. Now, if Hilda threw the dice 12,000 times, how many sixes would she expect to get? 12,000 multiplied by, what's usually our chance for rolling a 6? Rolling a 6 is 1 in 6, which is 2,000 times. You're expecting each one to turn up 2,000 times. 2001s, 2002s, 2003s, 2004s, 2006s. Okay, evenly spread across the numbers. Okay. Now, question 6. The result from 40 spins and a number of spinners were recorded as follows. They asked for you to complete this table. Now, does anybody know what a tally is? You ever see any of those prison movies where they're writing on the wall, counting how long they've been in jail? You'll see something like this. That represents 5. You only go up in 5s. So what does the number on the board represent? 7. What about this number here? 3. What about this one? Oh, wait. Broke my own rule. What about this one here? How many in total? 12. Oh, I have one too many, don't I? Yeah. There you go. So 12, yeah? Okay, perfect. So here's what we're going to do. How many number 1s do we see? So what you do is you mark them out. Every single time you count, you mark it out. 1, 2, 3, 4, 5, 6, 7. 7. 1, 2, 3, 4, 7. Are we happy with that? How many 2s do we have? I counted 7, and am I missing one? What? 8. Any other ones? 8, yeah? Now what about 3s? 3, 4, 5, 6, 7, 8, 9, 10. Okay, next one, 4s. 4, 5, 6, 7, 8, 9. I got 9. Who got 9? Okay. Now we'll know if we're right or wrong because we can add them all up at the end and make sure that it turns into 40. That's good inkling that that's good sign that you've got it right. And finally 5s. 2, 3, 4, 5, 6. Now, write down the frequency means how many times it happened. 7, 8, 10, 9, and 6. Add those numbers up together and what should we get? How many people were there? Oh, sorry, as in there was 40 spins, 40 turns. Okay, is that right then? Now, use these results to estimate the probability of getting a 3 with the next spin. How many times did we get a 3? 10 out of 40 spins, which is 1 in 4, right? Is the spinner biased? You can give two answers. You can say one thing is, if the spinner wasn't biased, if the spinner was perfect, let's say, how much would each one turn up? So you spin it 40 times. How many different outcomes do we have? 1, 2, 3, 4, 5. It's a 5-sided spinner. Yeah? Do you remember like where's my pentagon? Do I have a pentagon here? Oh, here we go. Something like this. Say, whoa, I get you. So, yeah, I gotta go to the center. So, something like that. It's not gonna be 100% accurate, but you get the gist. It's a 5-sided spinner. Everybody's happy with that? So you spin it around, and whichever side it lands on, brilliantly. But there's 5 different outcomes. If I do it 40 times, how many times should it land on each one? Divided by 5 is 8 times. It should land on it 8 times. Does it land on it 8 times all the time? One of them gets a 7, one of them gets an 8, one of them gets a 10, one of them gets a 9, one gets a 6. Would you think that's realistic? That isn't always going to land 8 on each one. Exactly. So you can say two things. You can say you can do one answer where you say, look, I think the number 6 and 10 are too far away from 8. Some people might say that. But what I'd say is that, look, you haven't spun it enough. Do you understand? If you haven't spun it enough, it isn't such a big gap. Like if you do it like hundreds of times, I reckon you'll see that will level out a bit more, won't it? Now, something I got to ask you, right? Let's say, for instance, in this example, the average is 8. Yeah, 10 is 2 bigger than 8. Now, imagine the average was 100. And one of them came up 102 times. Would that be such a big deal? That gap of 2. Why is it not? Why is it not such a big deal in this case? It's on a bigger scale. 2 extra, considering you already got 100, isn't such a big deal. So it's a bigger deal when the numbers are smaller. So long story short, always do more trials, more attempts to make your results more accurate. I would say it's too early. You haven't done enough tests to know whether if that spinner is biased or not. However, if this was a 0, what would you think then? There's strong enough evidence that it's biased. Okay? Now, number 7. Calculate the experimental probability of each letter. How many times did we spin it? 35, 43, 100 times. Also tells us that, doesn't it? Now, A turns up 14 out of 100. B turns up 43 out of 100. C turns up. D. And finally E. Now, do any of those fractions break down? That breaks down to? That stays the same. This one? 2 out of 25, good man. Next one? And 30 out of? Yeah, that's it. That's the red answers are the better answers, okay? Close to full marks for the blue answers. Definitely full marks for the red answers. Got it? Now, that's what's called the experimental probability. What probability actually happened in the experiment? If the spinner was fair, how many times would you expect each letter to occur? If the spinner was fair, lads, how many times did we spin it? How many different outcomes do we have? How many times should each one come up? They should come out 20 each time. Now, do you think the spinner is fair? What's stopping? There's one result that's really, really out of the ordinary. 8 and a bigger one than that? 43. The 8 and the 43 suggest that the spinner is biased because it's over twice the amount it should be. And it was spun 100 times, so it's too far out. Huh? Or the weight, it could be weighted. Like you could have like a lead weight in here if you're trying to rig a game. You put a lead weight inside the plastic and then you spin it, and then more than likely it'll hit B more often. So that's called rigging a game. Yeah. Okay guys,